Welcome to the Unit 1 Section 4 video on absolute value functions. Alright, an absolute value function is a function that contains an algebraic expression within absolute value symbols. So that makes a lot of sense, right? We have an absolute value symbol, and it's important to note that in an absolute value function, the absolute value symbols act as an operator. Okay, you may be inclined to think of them as like parentheses or brackets when you're doing things, but if you have a number outside of the absolute value, you're not able to distribute it. Okay, so the absolute value sign, which is indicated by two vertical lines on either side of some sort of expression, that is an operator, not just an organizer. Okay, like a set of brackets or parentheses would be. Recall that the absolute value of a number is its distance from 0 on a number line. Okay, so when presented with the absolute value of a number or a monomial, that term becomes positive. So here's just a couple of quick examples of some absolute values. So the absolute value of -5, it's 5 units away from 0, so the answer would be 5. Absolute value of -x would just be x, and the absolute value of 7 would be 7. So if you have a positive number in the absolute value symbols, then whatever is that value inside of it is just what your absolute value would be. Okay, so now let's talk about the parent function for an absolute value. Okay, the graph of an absolute value parent function is composed of two linear pieces joined together at a common vertex. Okay, and in the case of a parent function, it would be the origin. So let's take first this table. If we were to put -3 in for x and we took the absolute value of x here, then our y, or our f of x, would be 3. The absolute value of -2 is 2. The absolute value of -1 is 1. Absolute value of 0 is 0. Absolute value of 1 is 1. The absolute value of 2 is 2. And the absolute value of 3 is 3. So now that we have x and y coordinates, we can very easily graph what we have here. So we would start at the origin, 0, 0. And if we go on the positive side, we would end up with 1, 1, 2, 2, 3, 3. And that trend would continue on up. And so we would end up with a line from the origin that extends out with a slope of 1. On the other side, we have from the origin 1, -1, 1, -2, 2, -3, 3. And so our slope here would extend out from the origin going to the left, and that slope would be -1. And you notice that we're decreasing on the left, so it makes sense we would have a negative slope here, and we're increasing on the right, which means we should have a positive slope there. So this is our parent function. This is what it looks like when it is graphed. Okay, so keeping this graph in mind, that vertex is at 0. Let's talk about some of the key features of this parent graph, okay? And I'm going to have to take the graph off the screen, but hopefully you have made a sketch of that graph. If you have not, just rewind a few seconds and get a quick sketch of that graph down, either in your notes or on another piece of paper. And we'll describe some of the key features of this function. Okay, so with the function shape, well, it is shaped like the letter V. So it's shaped like the letter V. Okay? Our x-intercept would be at 0, 0. That's where the graph touches the x-axis. Our y-intercept is also at 0, 0. That's where it crosses the y-axis. Our domain, well, we're going infinitely from the left and infinitely to the right, so therefore our domain is -infinity to +infinity. Our range, if we go from bottom to top, remember range is the only one where we're using the y-axis values. If we go from the bottom, we first hit the function at 0, and then it extends on infinitely going up on either side to infinity. We include the 0 because it does touch 0. We have an x-intercept there. We also have a y-intercept there. So therefore we include 0 with the bracket. The absolute minimum of this function is at the point 0, 0. We'll come back to slope here in a moment. Positive interval, well, it's positive everywhere except for one place. It's positive from negative infinity to 0, and then from 0 to infinity. Why is 0 not included? Well, the value for x equals 0 is y equals 0. So it's not positive or negative, because 0 is not positive or negative, so therefore we do not include 0 as part of the positive interval. Where is it negative? Well, nowhere. So there is no negative interval. It increases from 0 to infinity. It's decreasing from negative infinity to 0. And then the end behavior. As x approaches infinity, so we're looking at the right-hand side, f of x approaches infinity because it's going up, right? As x approaches negative infinity, so now we're looking at the left side, it's also going up. So f of x goes to infinity. Okay? Let's head back to slope here. Well, the slope is different depending on which side of the graph you're at. It's -1 on the left side, and it's +1 on the right side. So I'm just going to notate it as the slope is plus or minus 1, and it depends on where along the graph you are. So now we know a little bit about the parent function. Let's talk about transformations on that parent function. Any absolute value function with a slope other than plus or minus 1, a vertex other than the origin, and or opens downward is simply a transformation of the parent function. So you may remember back in Unit 0 we talked about transformations of linear functions. We could translate it up or down. We could rotate it. We could reflect it. Well, we can do similar things to an absolute value function, but because it's more than a straight line, there's just a little bit more that we can do with it and other ways that we can describe it. So I'm going to start with the transformation that I think is going to be the most challenging here to keep straight. So what I'm giving you here is the structure of different types of things that can happen to your absolute value parent function. Remember, we start with f of x equals the absolute value of x. Well, we can multiply that absolute value by some value. We can add or subtract a value on the inside. We can add or subtract a value on the outside. So I'm going to go through what each of these things does. I'm going to start with the one I feel like is most confusing. So you have a translation to the right and to the left, as well as up and down. For a right-left translation, you translate to the right when h is positive, and you translate left when h is negative. So you'll notice that the h is on the inside with the absolute value symbols. Okay, so when h is positive, here's an example of that. F of x equals the absolute value of x minus 3. Well, you're probably thinking, well, wait a minute, I thought you said h was positive. There's a negative sign in front of that 3. You got to look back at this transformation template. We have the absolute value of x minus h. H itself is positive. It's positive 3. The operation that's being acted on that positive 3 is subtraction. So we're doing x minus a positive 3. So when you look at a translation to the right, it's going to look negative in the equation that you're given. I think it's a little bit clearer when we look at it in this context. What if h is negative? Well, here's an example of that. F of x equals the absolute value of x minus negative 3. Okay? H is clearly negative 3 here, and we're subtracting that negative 3 from x. What it's going to look like, because you are doing a minus a negative, it's going to look like the absolute value of x plus 3. And again, this is going to look opposite from what you think it should do. So when you see a minus in front, then we are going to the right. If you see a plus in front, we're going to the left. This is counterintuitive from what you think it's going to do, but that's because the operation on the inside of this template is subtraction. It's minus. Okay? So that's why these are going to look backwards from what they actually are. Now it gets easier from here. A vertical translation up, k is positive. You would think that if we're moving up, we're going positive. And if you're translating down vertically, k is negative, which again makes sense, right? And because the operation on this is positive, then it's going to look like what it should. It's going to be intuitive. So you have f of x equals the absolute value of x, and we're going to add 5 to that. Okay? That would be a translation up by 5 units. Similarly, an example of it being translated down, you would simply do minus 5 on the end. And that would be a translation down by 5 units. So I think the up and down translations are a little bit easier to follow than the left-right translations. Okay, so now we have a reflection across the x-axis. That occurs when a, which is that number out in front, when a is negative. So for example, f of x equals negative absolute value of x. Well, a reflection across the x-axis occurs when x is negative. Okay, so if you put a negative sign in front of the x within the absolute value symbol, so you have f of x equals the absolute value of negative x, then you have a reflection across the y-axis. And then finally, we can stretch and compress that V shape. The V shape is stretched when a, which is that number out in front, is greater than 1. It's compressed when a is some value between 0 and 1. Okay, so you've got some sort of fraction value that is less than 1. Okay, so examples of these, f of x equals 2 times the absolute value of x. That would be an example of a stretch. F of x equals, say, 1/2 times the absolute value of x would be an example of a compression. So these are all your rules. They are all here in one place for you. I think you get this a little bit more proficient at this if you do a few examples. So let's do just a few examples of these. So let's identify the transformations that occur to the absolute value parent function for each of these. All right, so for this first one, we have a plus 3 on the inside. So that means we are translated left 3 units. In fact, I'm going to make this a little neater for you so that it's easier to read. Okay, so we have it translated left 3 units. And then we have the minus 2 as well. So that minus 2 tells us that we are translated to the, or going translated down by 2 units. Okay. So now, let's go on to the next one. And let's talk about how this one is going to work. All right, so we have a negative on the x. So this particular function is going to be reflected across the y-axis. And then we have a plus 4, so that means it's going to be translated up 4 units. All right, so now we move on to the next one. This next one we have a 1/2 out in front. So this means we have a vertical compression to a slope of plus or minus 1/2. So plus or minus 1/2. And then we have a translation to the right by 7 units. And that's indicated by the -7 on the inside of the absolute value. Okay, for the next one, we have a minus sign on the front. So that's going to indicate that we have a reflection across the x-axis. So this is reflected across the x-axis. And then we have a -2 on the inside of the absolute value. So that means that we are translated to the right 2 units. And then we have a +5 on the end, which means translated up 5 units. Okay, moving to the next one. We have a 1/4 on the outside. So that 1/4 means that we have a vertical compression of to a slope of plus or minus 1/4. And then we have a +1 on the inside, which means we are translated left 1 unit. And then we also have a -1 on the outside, which means we're translated down 1 unit. And then finally, if we go to this last example here, we have a negative on the outside first. So that means a reflection across the x-axis. We have a 2, which means a vertical stretch to a slope of plus or minus 2. We are translated up, or I should say translated right, 3 units. That's indicated by the -3 on the inside of the absolute value. And then we have a +8 on the end, which means it's translated up 8 units. So those are just some examples of what we get when we translate or transform an absolute value function. These are different types of transformations that occur for each of these. Okay, well, now we've done it with equations, let's look at graphs. Okay, so we're going to do a similar thing here. We are going to determine what the translations or reflections or compressions and stretches, what all happens to these graphs by looking at them, and then we'll write an equation for that graph. So let's start with this first one. Okay, so for this first one, we can determine that we have a translation to the left, okay, and it's translated left by 5 units, so we have a translated left 5 units, and that's basically all that's happened. We just moved it over. The slopes are still the same. It hasn't been compressed. It hasn't been stretched. It has not been flipped or anything of that nature. So let's write an equation for this. So an equation that we can write for this is f of x equals the absolute value of x plus 5. Because remember, when you have a translation to the left, it's going to happen to that number in the inside of the absolute value, and it's minus a -5, so therefore it ends up being plus 5. All right, let's move on to the next one, and let's talk about the transformations that occur here. So for this one, we have a reflection across the x-axis, and we have a translation up 4 units. Okay, so it's been reflected, that's why the V is upside down, and it's been moved up 4 units. So we can come in here and we can write an equation, and that equation is f of x equals, now how do we take care of that reflection across the x-axis? We put the minus sign in front of the absolute value, and since our translation is up, we're going to be adding 4 to the outside. And so that would be our equation for the second example here. Okay, let's move on to the next two. So for C here, we have a vertical compression, first of all, to a slope of plus or minus 1/3, because we can figure out what the slope is if we look at the right-hand side. We're going up 1 over 3. So that's a rise of 1, run of 3. Rise over run gives us 1/3. And it's positive on the right side, it's negative on the third. And because it's between 0 and 1, we have a compression. We also have a translation down by 6 units. It's gone 6 units down the y-axis. So if we're to write an equation for this, well, we know that f of x equals, we know the 1/3 is going to go on the outside of our absolute value, and we have the absolute value of x, and when we translate up or down, it gets tagged on the end here, minus 6. All right, moving to this next one, we have 3 things happening. First of all, we have a vertical stretch to a slope of plus or minus 2. Again, you can figure this out by looking at the rise over run on the right side, or the increasing side. We rise 2, run 1. Rise 2, run 1. So rise over run, 2 over 1, that gives us 2. We've also translated it to the right and down. So we've translated right 3 units, and we've translated down 3 units as well. And so when we go to write our equation for this, we end up with f of x equals, our slope goes on the outside, so that's 2, and then our translated right is going to go on the inside the absolute value, so that's going to be x minus 3. Remember, minus going right. And then we're translated down 3 units, so we're going to put a minus 3 on the outside as well. Okay, 2 more examples on this page before we move on. Let's see what's happening with this particular function. Okay, so this one is got a reflection because it's upside down. So it's reflection across the x-axis. And then we're translated up the y-axis by 5 units. And we're also translated left by 3 units. So when we put all this together, we're going to end up with f of x equals, well, since we have a reflection across the x, we're going to have a minus out in the front. Since we're translated left, we're going to have x plus 3. And since we're translated up, we're going to have a plus 5 on the outside. And then this final example. This one is stretched. So we have a vertical stretch to a slope of plus or minus 3. Again, we check our slope here. Rise over run, rise 3, run 1, rise 3, run 1, rise over 1, 3 over 1, that gives us 3. And then translated down 7 units. Okay, and you see that going straight down the y-axis. Okay, so we can write an equation. F of x is going to be equal to, well, our slope goes on the outside, 3 times the absolute value of x, and then our translation down gets taken care of on the outside, the absolute value on the end, minus 7. All right, so let's pull some stuff together here. Now that we have been able to figure out what the transformations are when we look at a graph and when we look at an equation, let's use that information to be able to take an absolute value function and graph it. Okay, so we're going to start these with looking at where our vertex is going to be. And you may have noticed at this point that our vertex is placed wherever our left or right transformation is and wherever our up and down translation is, based from the origin, because that's where we start on the parent function. So on this one, we're translating to the left 1 and up 3. So our vertex is going to go right there. From here, it's just going to be a matter of drawing our lines and doing it properly from each side, because that's where our vertex is going to be. Well, we have a negative sign out in front, which means we're going to be reflected across the x-axis, and that means our slope is going to be flipped on either side, meaning we're going to have an upside down v. Well, our slope is 1, so that means from this side, we're just going to follow through going this way, and similarly on this side, we'll follow through going through this way. And that's our graph. That's all there is to it. We'd use our slope as our information, and you'll see that more in the second example. Okay, so here we have what happening? Well, we've got negative 2, so we go back, well, we go to the right by 2. That's going to be our left-right translation. It's going to be to the right because we have a negative 2. And then we have a negative 4, which means we're translating down. So this is where our point, our vertex, is going to be. And so from here, we just have to use our slope to determine how to draw this thing. Well, our slope out in front is 3, so that's going to be a rise of 3, run of 1. Rise of 3, run of 1, rise 3, run 1, rise 3, run 1. And so you end up with the line going this way. And then we do the same thing going the other way. Rise 3, back 1, rise 3, back 1, rise 3, back 1, rise 3, back 1, and you end up with your other end of your line going that way. So we have a function that's been vertically stretched and translated right and down. All right, so you've got these drawn. Hopefully you've sketched these for yourself. If you haven't, take a moment to pause and get these sketched down, because we're going to, while we have these, just figure out a couple of other pieces of information from them, such as domain and range. So let's start with this first one. The domain of this one, as always, we're going infinitely from the left, infinitely to the right. So in this case, our domain is going to be negative infinity to positive infinity. Our range, well, we go from bottom, and we're coming from negative infinity on both ends of this from the y direction. And as we go up, we hit a peak, the peak of this thing, at 3. And so our range is going to be negative infinity to 3, and we are including the 3 because it touches 3. All right, over here, let's find what our y-intercept is. Well, that's pretty easy to find. It's 0, 2. Let's find where we're increasing. Well, we're increasing on the interval from 2 to infinity because it goes infinitely to the right. And then we are decreasing from negative infinity to 2. So we'll fill that in here. Okay. So, once we graph these things, we're able to kind of pick out key features. That's something we're going to continue to do here along the way. All right, let's throw in a word problem. So, during a winter holiday sales, Target's sales steadily increased over the holiday weeks. After the holiday, the sales start to decline. The following function represents the amount of sales for time in weeks. Find the average rate of change over the weeks from 1 to 5. Okay, so remember when we're doing average rate of change, you're given your x1 and your x2. x1 is 1 and x2 is 5. We need to find y1 and y2. So the way we're going to go about doing that is to find out what y is by just simply plugging 1 into our function and finding out what the value is, and then plugging 5 into our function and finding out what the value is. So let's start with s of 1 to find out what our x1 is. So s of 1 equals negative 2 times the absolute value of 1 minus 4 plus 4,300. Okay, well, first let's do what's in the absolute value sign. 1 minus 4 is negative 3. And then the absolute value of negative 3 is 3. And then negative 2 times 3 is negative 6. And finally, if we subtract 6 from 4,300, we end up with 4,294. So you notice we didn't even need a calculator for that. The math was basic and easy enough for us to follow through. All right, let's move over to do s of 5 so we can find what our y2 is going to be. So s of 5 is going to equal negative 2 times 5 minus 4, the absolute value of that, plus 4,300. And then we have negative 2 times the absolute value of 1 plus 4,300. The absolute value of 1 is just 1. Negative 2 times 1 is just negative 2. And if you subtract 2 from 4,300, you end up with 4,298. Okay, so what we have just found out is we can call this x1, y1, and x2, y2. Our x1 is 1, and the y value that goes with that is 4,294. Our x2 value is 5, and the value that goes with that is 4,298. And yes, these numbers are still big, but you'll see that you don't really need a calculator for this, because all that we have left to do now is find the average rate of change. Change in y over change in x, or you may know it as y2 minus y1 over x2 minus x1. Well, y2 is 4,298. y1 is 4,294. x2 is 5. x1 is 1. And when we do this, we end up with 4,298 minus 4,294 on the top, that's 4. 5 minus 1 is 4. So our average rate of change is 1. That would be our answer to this problem. Okay, let's move on to this next section. We're going to solve some absolute value equations, and there's really not much to doing these. There's just a couple of things that you have to keep in mind when you're doing these types of problems, okay? First, you want to isolate the absolute value expression. Once you get that isolated, then you're going to split it up into two different equations. One where what's inside the absolute value is set equal to the positive version of what's outside, and then the negative version. And then you're going to solve both equations and check your solutions. So let's start by solving this first problem. Let's just do some examples. Well, the absolute value is already by itself, so that work's already done for us. So all we have to do now is split it up. You're going to have negative 3x minus 5 is equal to 14. And you're going to have negative 3x minus 5 is equal to negative 14. And then you're just going to solve both equations as you normally would. You add 5 to each side here, you get negative 3x equals negative 9. X equals 3 when you divide each side by negative 3. Same thing over here, add 5 to each side. That gives you 19. Actually, I did this backwards. Let me fix that. So we have negative 3x minus 5 equals 14. This would actually be negative 3x equals 19. And then you divide each side by negative 3, you get negative 19 over 3. This side is negative 3x equals negative 9. When you add 5 to negative 14, you get negative 9. So here you get x equals 3. Okay, so you're going to end up with two solutions. If you want to write it as one package, you can write it in set notation. The set of negative 19 thirds and 3 are your two solutions for this problem. All right, let's move on to example 6 here. Let's solve this one. Well, the first thing we have to do here before we split it up is we got to get the absolute value by itself. And we do that by adding 10 to each side. So when you add 10 to 32, you get 42. And now we're going to split it up. You have negative 7x plus 7 equals 42. And negative 7x plus 7 is equal to negative 42. Okay, so when we do this left equation, we get negative 7x equals 35. When you subtract 7 from each side, divide each side by negative 7, x equals negative 5. Similarly, on the other one, negative 7x equals negative 42 minus 7, so that's negative 49. Divide each side by negative 7, you get x equals 7. So your set of solutions would be negative 5, 7. All right, let's move on to this last example on this page. We have 3 minus 8x plus 2 equals negative 43. All right, so first, let's get the absolute value by itself. So we have the absolute value of 3 minus 8x. When we subtract 2 from each side, you get negative 45. Well, let's stop right here. Is it possible for us to take the absolute value of something and get a negative answer? Well, no. We cannot have a negative value on this side. If we're taking the absolute value on the left-hand side, we can't end up with a negative value here on the right-hand side. So at this point, we can just stop and say that there's no solution, because this is not possible. All right, let's do one more example here. We've got this absolute value equation that we want to solve. First thing we got to do is get the absolute value by itself. So to do that, first we're going to subtract 8 from each side. So when we do that, we end up with what's left on the left-hand side equaling negative 52. And then when we divide each side by negative 4, we get the absolute value of 3 plus 10x is equal to 13. Now this we can split up because we have a positive number on the other side of the absolute value. So now we'll split it up from here. 3 plus 10x equals 13. 3 plus 10x is equal to negative 13. We are going to subtract 3 from each side, so we've got 10x equals 10. So x equals 1. And then on the other side, we've got 10x equals negative 16. So x will be negative 16 over 10, which can be reduced down to negative 8/5. And so your solution set here would be negative 8/5, 1. So solving absolute value equations are fairly straightforward. Now let's talk about solving absolute value inequalities. So to solve an absolute value inequality, first you want to isolate the absolute value expression, which is what we did in the equations. And then you use the quantity inside the absolute value notation with the original inequality and the original quantity. Okay, so essentially you're going to take the inequality that's presented and you're just going to rewrite it without the absolute value symbol. That's all this step is. Now the other one, you're going to have to take the opposite of the original inequality. So if it's greater than, it becomes less than. If it's greater than or equal to, it becomes less than or equal to, and vice versa. And you have to take the opposite of the quantity on the other side. So if it's positive, it becomes negative. If it's negative, it becomes positive. Okay? The nice thing here is all the changes are going to happen to the same side. Okay? So one you're going to do with the original, just like it is, just drop the absolute value. And on the other, you'll drop the absolute value, but then you'll change the sign of the inequality, then you'll change the sign of what's on the other side of the absolute value. And you'll see that here in these examples as we do them. The other thing that you have to figure out is what statement are you going to put between the two inequalities. So we're going back to talking about compound inequalities here. And if you need a refresher on that, that's in the section 1-2 video on compound inequalities. So we got to either put an or in between or an and in between. So you put a or in between for a union statement if the absolute value is greater than or equal to a quantity. And then you use an and statement if the absolute value is less than the quantity. Okay? So if the absolute value is on the left-hand side, like most of these are set up, then you're going to use something that kind of looks like this. And comes first alphabetically, or comes second. If you stick your things in between, the one that points to and here, that's and, so the one that's less than. If it's greater than, then you're going to use an or. Okay? This is just something that you have to remember. It's something that is going to take a little bit of practice, but we'll do a few practice problems to hopefully help cement this into your memory. Okay? So let's start off by solving this inequality. Well, first of all, the absolute value is already by itself, so we're good there. So all we have to do is split it up. We're going to write it exactly the way it is, just without the absolute value symbols. And then we're going to write it where we flip the sign and change the sign. Okay, flip the sign of the inequality, change the sign of the thing on the other side of it. Okay, so flip the sign, change the sign. And so then we just solve each one. Before we solve them, we need to figure out, are we putting and or in between? Well, since it's greater than, then we're going to put or. It's greater than or equal to, but we're mainly looking for, is it greater than or equal to? And now we're going to solve, and we've got x is greater than or equal to, we subtract 5 from each side, we get 7 for this one. Subtract 5 from each side, and we get negative 17 for this one. So now it's just doing a compound inequality. We're going to do our test number line. Our points of interest are negative 17 and 7. All right, for the first one, we have x is greater than or equal to 7, so we do a solid dot going to the right. And then for the other one, we have x is less than or equal to negative 17, so we have a solid dot going to the left. And so since it's an or statement, we're going to include everything. And so we are just going to write down everything that we have graphed up here in our sketch. So we got a solid at negative 17 going to the left, and then we've got a solid at 7 going to the right. Okay? In set notation, we have the set of all x such that x is less than or equal to negative 17, or x is greater than or equal to 7. And in interval notation, we have negative infinity to negative 17. It's included, union with 7 to infinity. Okay, we're just going to do a few more of these examples. Let's solve this one. We have the absolute value of x minus 8 is less than negative 2. We're going to add 8 to each side first. So we have the absolute value of x is less than, we're adding 8 to each side, so it's going to be less than 6. And then we just have to split it up. There's nothing else really to solve. So we got x is less than 6. We have x is greater than negative 6 because we flipped the sign, changed the sign. And we have an and statement in between because it's a less than statement. So we're going to sketch our graph. We have negative 6 and we have 6. So for the first one, x is less than 6, so we have open dot going to the left, and then we have x is greater than negative 6, so we have an open dot going to the right, and since it's an and statement, we're going to do what's shared. So on our answer number line, we're going to have negative 6, we're going to have positive 6, and we are just going to do what's shared. So we have our open dot at negative 6, we have our open dot at positive 6, and we just shade what's in between. For our set notation, we can actually combine this into one statement if we want. Set of all x such that negative 6 is less than x, which is less than 6. And then in interval notation, we have everything between negative 6 and 6, but not including negative 6 and 6. Okay, example 11. We got to get the absolute value by itself first, so we're going to subtract 7 from each side. So we end up with greater than or equal to 4. And then we're going to divide each side by 4. That gives us the absolute value of x minus 10 is greater than or equal to 1. And then we're going to split it up. We have x minus 10 is greater than or equal to 1. We have x minus 10 is less than or equal to negative 1. And then we're going to add 10 to each side. So we have x is greater than or equal to 11. And then we have x is less than or equal to 9. And we didn't put what we put in between. Since we have a greater than or equal to, when we get to the absolute value being on one side by itself, then we are going to be doing an or statement. So now let's do our sketch. Our points of interest are 9 and 11. Our first one, x is greater than or equal to 11. So we've got solid dot going to the right. X is less than or equal to 9. So we've got a solid dot going to the left. And so since it's an or statement, we are including everything along the line. So when we do our final answer line, we are going to have a solid dot at 9 going to the left, and a solid dot at 11 going to the right. In set notation, no other way to write it other than the set of all x such that x is less than or equal to 9, or x is greater than or equal to 11. And then in interval notation, we have negative infinity to 9, including the 9. We're going to include the 11 and go to infinity. All right, in example 12, we're going to solve this one. So again, we are going to start by getting the absolute value by itself. So we subtract 6 from each side to begin. So you get negative 2 times the absolute value of x plus 10 is greater than or equal to negative 2. Then we divide each side by negative 2. Now this is an important example here because we're dividing by a negative. These rules remain the same. We're still going to flip the sign here, and that'll give us less than or equal to 1. And then from here, we can split it up. X plus 10 is less than or equal to 1. X plus 10 is greater than or equal to negative 1. And since we are going by this line where the absolute value is by itself, we are going to use the AND statement because we are using less than here. Okay, so that's important. You're going based off of the inequality once the absolute value has been isolated on one side. And then from here, we're just doing a little bit of solving. X is less than or equal to negative 9 when we subtract 10 from each side. This one, we also subtract 10 from each side, and we get x is greater than or equal to negative 11. All right, let's do a little bit of sketching. So we've got negative 11, and we've got negative 9. The first one, we are x is less than or equal to negative 9. The second one, we have x is greater than or equal to negative 11, which looks like that. And so when we do our final one, we want to do what's shared because it's an AND statement. And so we're just going to do a solid dot at negative 11, solid dot at negative 9, and it's everything in between because that's what's shared. In set notation, again, we can compress this a little bit and do negative 11 is less than or equal to x, which is less than or equal to negative 9. And in interval notation, we have the set from negative 11 to negative 9, including both of the ends. Okay, so along to the last page of notes for this section and really for the unit. Let's do a couple more of these examples. So let's solve this one. Well, we have a fraction, but that's not really an issue because we got to get the absolute value by itself, and we multiply each side by 2 to do that. And so we immediately lose the fraction for those of you who are a little nervous about fractions. And we end up with less than or equal to negative 4. From here, we split it up. We have 8 plus x is less than or equal to negative 4. We have 8 plus x is greater than or equal to positive 4. Again, flip the sign, change the sign for that second one. Now, in this one, we're pointing to the left, or we're doing less than, so we have an AND statement. And we're just going to solve. So we subtract 8 from each side on this one. We get x is less than or equal to negative 12. Subtract 8 on this one, x is greater than or equal to negative 4. So let's sketch what that looks like. We've got negative 12. We've got negative 4. For the first one, we have x is less than or equal to negative 12. For the second one, we have x is greater than or equal to negative 4. And since it's the AND statement, we do everything that is shared. Well, there's nothing that's shared. So whatever line that you're provided with, it may have some tick marks on it for you already. You're just going to leave it without anything being plotted on it at all. Now, since there are no solutions in interval notation, we just say there are no solutions. And then in set notation, we have our two options of how we notate that, either with the curly braces that are empty, notating the empty set, or you can do the 0 with the slash in it. That also indicates the empty set. All right, final example, that's a straightforward example here. Let's solve this one. Well, this one's already isolated for us, so all we have to do is split it up. 6x minus 3 is greater than negative 63. 6x minus 3 is less than positive 63. So on the first one, we're going to add 3 to each side. So we get 6x is greater than negative 60. And then x is greater than negative 10. And then on the other one, add 3 to each side. You get 6x is less than 66. So x is less than 11. Now, we look at the original one where the absolute value is isolated. And this is going to be an or statement because it's greater than. So let's sketch what this looks like. We've got negative 10 and we have 11. Well, for the first one, we've got greater than, so that's going to go this way. For the second one, we have less than, so that's going to go this way. And we do everything because it's an or statement. So since we do everything, whatever number line you're presented with, it may have things labeled on it for you. You're just going to go through and you're going to just trace over the entire number line. In set notation, this is the set of all real numbers. And in interval notation, it's negative infinity to positive infinity. Okay, so let's wrap up this section with a word problem. Just to kind of give you an idea of how to use absolute value inequalities in a real world sort of a situation. So we have a manufacturer of boat motors, and it has specification for parts given within given tolerance limits. If a part is to be 3.2 inches wide with a tolerance of 0.01 inches, this means it must be at least 3.19 inches wide or at most 3.21 inches wide, okay? Because if you subtract 0.01 from 3.2, you get 3.19. If you add 0.01 to 3.2, you get 3.21. So that's kind of our range of acceptable widths. This tolerance limit can be expressed by an absolute value inequality, which is presented here. So this whole top part is basically just a little bit of setup telling you how it works and how it looks within an absolute value setup. So now what we're going to do is we're going to use that to find the maximum minimum acceptable dimensions of a part. So it's like this 3.19 and this 3.21. Those are the minimum and maximum acceptable values. So we are going to set up an equation like the one that they presented here with this information. So it's supposed to be 7.32 centimeters long. That's the perfect length. The tolerance is 0.002 centimeters. And I know that sounds like a very little amount, but that's a very real world sort of a tolerance level. Because if you think about it, if you have a motor, that boat motor that is being held together by nuts and bolts, that nut and that bolt have to fit perfectly together. Otherwise, the whole motor could come apart. So it has to be very precise, and this is kind of what this problem is driving home, and you have to have this level of precision. If a part is made without that level of precision, then it gets thrown out and they have to remake it. Okay, so let's use this information to set this up. Well, we know that we're going to be talking about a length, or let's just continue to use W for width. It's fine. You know, we're just using a variable here. And we are going to subtract what it's supposed to be, okay? Because here it was supposed to be 3.2. Here it's supposed to be 7.32. So we're going to subtract that here. And then it's got to be less than or equal to whatever our tolerance level is, which is 0.002. Okay? So now we're going to take this and we're going to solve it for W and find out what our two values for W are. Those are going to be our boundary points. So let's split it up like we've been doing. We've got W minus 7.32 is less than or equal to 0.002. Since we have a less than, this is going to be an and statement. And then our other one will be W minus 7.32 is greater than or equal to negative 0.002. Okay, now we're just going to solve. All we have to do is add 7.32 to each side on both of these. So on this one we get 7.322, And then on this one, we get W is greater than or equal to 7.318. Okay, so this gives us our minimum and maximum. So our max is going to be 7.322 centimeters. And then our min is going to be 7.318 centimeters. And that's all there is to that half of the problem. Now on the other side, we want to find a tolerance if a part must satisfy this inequality, okay? So we have the min and the max already as part of this compound inequality. We want to go the other way and find out what the equation would be. And if we can find out what the equation will be, then we can find out what the tolerance would be, because that's on the right-hand side of this inequality, okay? So all we have to do is start off with this compound inequality that they give us. Once we have that, let's figure out a value that we can subtract so that we have something that is the same value away from the number line on either side. Well, what we are looking for is perfection, and perfection sits halfway between the minimum and maximum values that it can be. So how do we find the minimum and maximum values? Or how do we find that perfect value in between that's halfway between these two? Well, you could take these two values, add them together, and divide by 2 to get the average, which would be what sits in the middle. And that happens to be 5.21. So we're going to subtract 5.21 from everything, okay? And when we do, we get negative 0.03 on this side. We get W minus 5.21 in the middle. And then on this side, we get 0.03. So this can be rewritten as, since this is a compound inequality, this can be rewritten as W minus 5.21 is greater than or equal to negative 0.03, and W minus 5.21 is less than or equal to 0.03. Okay, and that's the one that's kind of kept the same. This is the one where we flip something, because this looks very much like the format that we want. This one is the same thing, just with the sign flipped and the inequality flipped. Okay, sign of 0.03 is changed to a minus, and we flip the inequality. So from here, we can write it as the absolute value of W minus 5.21 is less than or equal to 0.03. And what's on the right-hand side is our tolerance. So our tolerance is 0.03 centimeters. So we can go either way with these. This is just a little bit of a real-world application of an absolute value inequality and where you would find something like this. So that wraps up Section 4 of Unit 1, and it also wraps up Unit 1. The next video in this series will be Section 1 of Unit 2.